Um, Jerry's away this month, and I think in honor of Leap Day, we have an extra special speaker. We have Assistant Professor Michelle Muth from the University of Washington to give a talk on sulfur and iron oxidation states in volcanism. I'll remind everyone to mute yourself and to, if you have questions during the talk, to enter them in the chat, and then it breaks at 20 minutes or 40 minutes or the end. I'll call on you to ask your question. I'm Michelle. So Michelle, welcome and take it away.
All right, great, thank you. Okay, well, thank you so much for the invitation to come and speak today. I am very excited to talk about some work that I've been doing with collaborators investigating how sulfur and iron valence state affects the way that we study and think about Earth's volcanism. Before I jump into the science of it all, I want to take a moment and acknowledge everyone who's helped make this project possible. So this work was done during my postdoctoral fellowship at the Smithsonian National Museum of Natural History with Elizabeth Cottrell, Tony Lanzarotti, and Matt Newville at GSE Cars also definitely helped make this work possible and were extremely helpful. So I would like to acknowledge all of their incredibly useful contributions, without which this work would not have been possible. Okay. So I'll back up by talking in the super big picture about why we want to understand these seemingly very detailed aspects of sulfur and iron in silicate melts. And it actually ties into these very big picture questions in the earth sciences. So I've always been fascinated by this photo of a volcanic eruption in the Kuril Islands taken in 2009. This eruption was taken from the International Space Station. They just happened to be at exactly the right point to capture this incredible photo. I've liked it not only because it's incredibly visually striking, but also because it illustrates really well the close relationship between Earth's volcanism and our atmosphere and how intimately linked those two systems are. And that link is incredibly interesting when we hold in our minds at the same time that Earth's volcanism is also deeply rooted in our Earth's mantle. And I think there's no more concrete and better visualization of this than mantle xenoliths. So mantle xenoliths are chunks of the mantle that become entrained in volcanic eruptions. What I'm showing here is an outcrop of a lava flow in Hawaii that is just chock full of these green mantle xenoliths. So what you're seeing is the gray lava flow matrix, and then embedded in that lava flow are actually little chunks of Earth's mantle peridotite that were carried out into that lava flow during eruption. So due to observations like this and an incredibly rich history of studying this field, we know that Earth's volcanism is rooted in our mantle and is deeply connected to the Earth's interior. And I find holding these two perspectives together incredibly valuable because it allows us to zoom out and think about this broad view of volcanism in our planet. And one of the grand questions in my field of igneous petrology and igneous geochemistry is, how do these two reservoirs interact with each other through volcanism? In other words, how does the mass exchange that we know takes place in Earth's interior manifest at the surface of our planet? And to illustrate this, I'm showing a very zoomed out schematic cross-section of Earth's mantle in the green, crust in the gray, oceans in the blue, and atmosphere in the white. And I'm highlighting two key tectonic settings within this big picture view. So the first tectonic setting is volcanism at mid-ocean ridges. So these take place on the seafloor. They're generated through decompression melting of the Earth's mantle, and they're kind of our baseline style of volcanism. This is a style of volcanism that takes place on our planet, but we know also takes place on other planets. It has its own rich complexities, but overall, we understand it fairly well. And so we can think of this as our kind of baseline vanilla point of comparison when we're thinking about volcanism on our planet. And we contrast that with the type of volcanism that we know takes place at volcanic arcs. So volcanic arcs are formed in another type of tectonic setting, a convergent tectonic setting. In these settings, we have one tectonic plate diving beneath the other, subducting beneath the other. That tectonic plate releases water into the overlying mantle, and that water lowers the melting point and generates partial melts. And it's those partial melts of the Earth's mantle that rise up into the crust, become magma bodies that can eventually erupt in arc volcanoes. And so, as you can imagine, this system is quite a bit more complex than the system beneath mid-ocean ridge basalts. And so in this kind of framework that I'm setting up, we can think of arcs as our test case. So what is it about the process of subduction and the influence of those plate-derived materials that drives the differences that we see in arc volcanism? We can start out thinking as broadly as possible about these differences in the style of volcanism. So we know that at mid-ocean ridge basalts, volcanism is dominated by these effusive eruptions of pillow basalts. So these are these really interesting lumpy lava flows that erupt at the seafloor. You can see why they're called pillows, right? They have this pillowy, lumpy morphology as that basalt erupts on the seafloor and becomes rapidly quenched. And we know that this is the style of volcanism, an eruption style that dominates at mid-ocean ridge basalt spreading centers. We can contrast that with the type of volcanism that dominates at volcanic arcs. So at volcanic arcs, we see a much different style of volcanism. It's often concentrated at single stratovolcanoes, and it's often explosive. And in the United States, there's perhaps no better example of arc volcanism than Mount St. Helens, and particularly the eruptions of Mount St. Helens in the 1980s. So we know that volcanic arcs, like the volcanic arc that is located here in the Western United States, in Mount St. Helens, are typified by these explosive volcanic eruptions. And the field of earth science has made an incredible amount of progress in understanding how the process of subduction influences this eruptive style. We've learned that it is the presence of volatile elements like water and chlorine and sulfur that drive these eruptions towards a more explosive nature. And so I'm always amazed when I step back and think about just how much progress we've made in understanding these relationships over a relatively short period of time and kind of scientific history. That being said, there's still quite a bit of work that we have to do. There's still a lot of things we don't understand. And one of those aspects of Earth's volcanism is oxygen fugacity. So oxygen fugacity is a parameter that's a little bit more esoteric in comparison to things like pressure and temperature that we often think about. But as I think this audience is probably aware of, oxygen fugacity, the redox capacity of different materials, is an incredibly important part of understanding any chemical system. And in earth sciences, we tend to express magma redox state or silicate melt redox state in terms of oxygen fugacity or FO2. So that's based on the partial pressure of oxygen, and it's just a broad means of expressing the availability of oxygen to participate in chemical reactions. So it's just the thermodynamic convention that we use most often. And we've known for a large part of the history of this field that oxygen fugacity, automatic lights. Oxygen fugacity is an important parameter in how we think about our system. So this is an experimental study from the 1960s showing the stability of anite, which is a mica mineral. And you can see that in addition to more closely easy to measure parameters like pressure and temperature, oxygen fugacity has a clear effect on the stability field. So we know that oxygen fugacity is very important to understand, but it can be a little bit tricky to measure in Earth materials. So we know that there's some big picture questions about magma redox that we need to understand. And one example of that is the offset in the oxygen fugacity of mid-ocean ridge volcanics in comparison to arc volcanics. So this is one of the first papers to investigate this picture in detail. What this plot is showing is a compilation of oxygen fugacity, or FO2, measured in volcanic rocks for mid-ocean ridge basalts in this white data set and arc volcanics in the two data sets furthest to the right. You'll notice in this case that oxygen fugacity is expressed relative to this buffer system, so it's expressed as delta NNO values. For this talk, all you really need to know is that these higher delta NNO values means that the system is more oxidized. So we've known for a long time that there are these big picture differences in magma redox state that seem to vary as a function of tectonic setting. And the reason why we're able to make these observations has to do with our ability to measure the valence state of iron. So iron is one of the most abundant elements in Earth's crust and in Earth's magmas. This pie chart to the right is showing the abundance of elements in Earth's crust. You can see that iron is a fairly significant component of this. Iron is also present in two different valence states in silicate melts and in silicate minerals on our planet. So it's present both as Fe3+ and Fe2+, and we can take advantage of that by measuring the proportion of those two valence states in silicate melts and use that to calculate oxygen fugacity. So the question becomes how to measure the valence state of iron. For a long time, the best method that we had available was wet chemistry of measurements of iron valence state. So this involved dissolving volcanic rocks into solution, then using titration methods to determine the proportion of Fe3+ and Fe2+. This method is extremely precise, but the downside is that it's fairly time intensive and it's fairly material intensive. So there's a limit in the types of data and the types of materials that we can analyze using this approach. And one of the materials that's hard to target with this approach is volcanic glass. So volcanic glass is an extremely valuable way to study the chemistry of magma bodies. There's two areas on our planet that preserve volcanic glass really well. One type of volcanic glass sample that we use a lot is called a melt inclusion or glass inclusions. These are inclusions that form in natural crystals as they form in magma chambers in our Earth's crust. And then when that magma chamber evacuates and that parcel of silicate melt that's trapped in that crystal quenches to a volcanic glass. And we can use that volcanic glass to learn things about the pre-eruptive magma chemistry. We can also take advantage of seafloor pillows, which also record minimally degassed magma chemistry. And this is because seafloor eruptions take place under about 4,000 meters of water. And so erupt under a little bit of pressure that helps contain some of the volatile elements that would otherwise degas during eruption. And on the rims of these pillows are little chips of glass that have quenched rapidly enough to preserve the original chemistry of that magma. And so these are incredibly valuable, very direct means to study magma chemistry, but the pools of glass are very small. And so they require another technique to access information about valence state. And so one of the most exciting developments in the field of igneous petrology has been the ability to target these glass samples using techniques like XANES. So iron XANES has developed as one of the best ways to determine the proportion of ferric and ferrous iron in volcanic glass in an in situ manner and with a small beam cross-section. The application of XANES has allowed incredible strides in understanding magmatic FO2 and how it ties into all of the volcanic processes that we're interested in studying. So what I'm showing here is a attempt at providing a comprehensive overview of all of the incredible data that's been produced over the last few years And of course, I still had to leave a lot of great studies out, but I wanted to show just how many parts of volcanism that this technique has allowed Earth scientists to access. So we've learned about magma oxygen fugacity and the chemistry of subduction zone magmas and volcanic arcs, during the degassing of magmas, during the process of mantle melting, and we've also been able to explore heterogeneity in Earth's mantle. So all of these super important big picture questions we've been able to study in the context of FO2 due to the application of iron XANES. So it's incredibly exciting, but there's a critical point to consider in all of this work, which is that the studies that I've shown here all make the same critical assumption. They're assuming that the proportion of ferric ferrous iron in these volcanic glasses is the same proportion of ferric and ferrous iron that was present in the high temperature silicate melt. And so it's this critical assumption that I want to revisit in this talk. Is this true, and can we rely on this assumption in how we interpret volcanic glass data? And we've known that there's some processes that can affect this assumption for a while. So processes like the degassing of magma, the loss of volatile elements, processes like the crystallization of magma bodies, those can both affect that assumption. And there's a body of literature that thinks through how to take those into account. But what's less well understood is the effect of this process of cooling and quenching of high temperature silicate melts, and whether or not this can also undermine the same assumption. And the reason why there's reason to have concern about this assumption is that sulfur and iron, we know, exchange electrons in silicate melts. So I talked about the presence of iron in silicate melts and how we take advantage of it. Sulfur is also present in silicate melts in significant quantities. It's more of a trace element, so it's present in about a factor of 10 lower concentrations than iron, but it's present in two very different valence states. So sulfur in silicate melts is present as S2- and S6+. And so you can imagine that that large difference gives it quite a bit of kind of oxidative leverage when it interacts with iron. So at the most extreme case, right, 1 mole of iron could oxidize, or excuse me, 1 mole of sulfur could oxidize 8 moles of iron. So if sulfur and iron are exchanging electrons during cooling, as some thermodynamic calculations suggest, it could really throw off our interpretations of iron XANES data. And so to illustrate that in more detail, I'm showing an example here of one of the proposed cooling models in comparison to the natural data we have. So what this plot is showing is the sulfur and iron valence state in silicate melts on the X and Y axis. And then each of these gray lines is an equilibrium calculation of the sulfur and iron valence state in that melt as a function of temperature. So it's predicting the equilibrium exchange between sulfur and iron as a function of temperature. And again, this model is proposed a few years ago based on some our kind of best guess based on the thermodynamic data we had available. What I'm showing in this green symbol is a representative value of the measurements that we can take of volcanic arc glasses. So usually melt inclusions from volcanic arcs. You can see that they're fairly sulfate rich and that they have roughly 20% ferric iron in them. And so using this equilibrium calculation, we can predict what would happen during the transition from high temperature to cooling down towards the glass transition, which is around 700 degrees or so. You can see that if we forward model what we would expect when cooling is taking place, we'd expect a large change in iron valence state accompanied by a decrease in the proportion of sulfate. So again, consistent with that overview reaction that I showed a few slides ago. So if this calculation is true, it means that there's some really significant changes taking place during the cooling of high temperature melt to a silicate glass that we need to take into account. In a lot of ways, volcanic arc glasses would be the most susceptible to this cooling effect because they have a lot more sulfur and a lot more sulfate than glasses from many other settings. But if we do the same calculation for glasses from other settings, so ocean island basalts in purple, back arc basalts in red, and mid-ocean ridge basalts in blue, we see that there's still an appreciable effect due to this cooling. And to provide some context in case these numbers are kind of meaningless to you, I'm plotting here the total range of iron valence state that's been measured in mid-ocean ridge and arc glasses so far. So you can see that this cooling effect, if it does take place, spans almost the entire range of measured values currently, and is therefore critical to understand and to test more rigorously. And so this makes us arrive at kind of the key question that's driving this work, which is, do sulfur and iron exchange electrons during cooling, and does this lead to measured changes in iron and sulfur valence state? So this is my pause moment here if anyone has any questions.
Great, thank you for the wonderful introduction. Are there any questions? If you have them, this is a great time to put them in the chat. I'll ask one, I think a simple one. So I think you mentioned this, but it also seems like there might be a difference in how much a difference between arc melts and mid-ocean ridge and how much they degas. Is that also a secondary or a similar effect for, in addition to cooling rate? It seems like you're saying they cool at different rates, but they also degas at different rates.
Yeah, there's definitely a big difference in how they degas, both due to how much volatile elements they hold in the first place, and also where they tend to erupt. So since mid-ocean ridges almost always erupt at the seafloor, they're a little bit more protected. And it is the case that degassing can drastically alter the redox state in a way that interferes with interpretations. And there's some authors, including Katie Kelly and Liz Cottrell, but also Eve Musalam, that have documented that. So it is an effect that we know is important, but it's kind of a separate mechanism from this cooling effect that I'm talking about here, but it's also important.
Okay, great. Matthew, Marcus, do you want to ask your question?
Yeah, I was wondering. There's many methods used to read iron Zane spectra to get valence, both at the K and L edges. What's your favorite and why?
I'm going to get into the methods in the second half of the talk.
Okay.
So great question, but yeah. I'll save that question to the end, and if it doesn't answer, then I'll talk more about why it's my favorite.
Okay, cool.
That sounds like a great motivation to continue and let us know. Okay.
Okay, sounds great.
Thanks.
Yeah, great cliffhanger. Okay, great. So we have our question, and now we need a means to test our question. Turns out that sulfur is fairly difficult to work with experimentally. And so it's really kind of tricky to test this question. What we're going to do to tackle it is use nature as an experiment for us. So we're going to go back to thinking about these pillow basalts that erupt on the sea floor and use them as a natural experiment. So as I mentioned, these pillow basalts can quench to glass extremely rapidly because we have this fresh basalt erupting right onto this cool seawater. Hopefully this GIF is somewhat legible to everyone who's seeing it. I think videos like this bring home just how kind of fresh, quote unquote, fresh these glasses are. So these are extremely rapidly quenched on the seafloor. And in some ways, some of the most rapidly quenched glasses that we have access to in the natural record, at least. And so if we take one of these pillows and we make a tiny slice of it, we make a little thin section of it, and we take a transect from the most rapidly quenched exterior of the pillow down into the more slowly cooled interior, we get a sample that looks something like this. So this is a natural pillow basalt from a mid-ocean ridge, and it's polished down to about 80 microns thickness, so you can see through the glass and you can see the crystals really clearly. And even qualitatively, you can see the difference in cooling rate that this glass has experienced. So we have this rapidly quenched super glassy rim grading down into the slowly cooled, more crystal-rich interior, where those crystals had the time to grow as the glass was cooling, or excuse me, as the melt was cooling down to a glass. We can use a half-space cooling model to calculate some average cooling rates that each of these, points within the transect might have experienced. And from this calculation, we can see right away that this pillow basalt has experienced a wide range of cooling rates. So there's several orders of magnitude of differences in cooling rate in this pillow basalt, but the whole pillow basalt has the same composition. So this is a great natural experiment to isolate cooling rate while keeping composition constant. And so again, with this sample, we can say, does iron and sulfur valence state vary as a function of cooling rate in the sample? In other words, would we expect a change in iron and iron and sulfur valence state as we grade down this pillow basalt transect? So that's our challenge here. And we're going to use two samples to answer this question. One is a pillow basalt from a mid-ocean ridge. Again, these are kind of vanilla baseline style of volcanism. This work takes advantage of a prior data set that Elizabeth Cottrell and Katie Kelly collected in 2011, which established that as we grade down this transect, there's no observable changes in iron valence state. The question is whether or not this is due to the lack of sulfate. So would we even expect this electron exchange reaction to be occurring in something like a mid-ocean ridge basalt? So we're going to revisit this sample and see how much sulfate is present using sulfur XANES. And we're also going to target another pillow basalt that is more prone to these quench effects. So back arc basalts are back arc spreading centers still take place under the seafloor, and so still erupt as pillows, but they're associated with arc volcanism, and so their chemistry is a little bit different. And importantly, they tend to be more oxidized and have more sulfate. So we're going to take advantage of this back arc pillow to test whether or not sulfur and iron are exchanging electrons in this more sulfate-rich composition. Okay, so now we'll get into the meat of it, the XANES analyses. So we used sulfur XANES to measure the valence state of sulfur in silicate glass. And we did this at GS-ECARS at APS. To get into the conditions a little bit more, we used a helium atmosphere. So that was that plastic bag in the last photo. And we attenuated the beam flux and increased the beam size to decrease the amount of photons hitting the samples to the extent that we were able to. And I'll talk about why we did that in a little bit. So we ended up using a fairly large nominal beam size of about 50 by 50 microns. We used the setup in fluorescence mode, scanned between 2437 EV and 2544 EV in sulfur XANES region. And importantly, we targeted only optically clear glass pools. So we're only analyzing the glass portions of these samples. So, so the main technical challenge in working with these types of samples, natural glasses, is that they're pretty unhappy to be on the surface of the planet. And so they're very prone to beam damage during all sorts of analyses. In the case of XANES, where we have this high intensity X-ray beam, we know that sulfur XANES can cause beam damage if we're not careful. To orient you to what sulfur XANES looked like in volcanic glass, I'm showing here two spectra for your reference. So these are experimentally synthesized basaltic glasses that we conducted sulfur XANES analyses on. The one in blue was a spectra taken on an extremely reduced experimental glass, where all the sulfur is present as S2-. So you can see that broad kind of peak/hump associated with sulfide. The red spectra was taken on extremely oxidized basaltic glass, and all of the sulfur is present as S6+. And so we have this extremely sharp peak associated with sulfate. So that's just to orient you to the features we'd expect to see. The good news is that they're extremely easy to distinguish from each other, which works in our favor for this application. So the challenge when working with glasses and doing sulfur XANES analyses on them is that they are prone to beam damage. This was documented clearly, I guess, a while ago now, maybe a couple decades ago now, by several groups, but they all found the same thing, which is that when they analyzed sulfur XANES in silicate glasses using an extremely high intensity focused beam, they realized that they were finding an ingrowth of this sulfite peak. Hopefully everyone can see my cursor, the sulfite peak here, and that it often grew at the expense of the sulfate peak. So there seems to be an ingrowth of sulfite or S4+ at the expense of sulfate in volcanic glasses when they're exposed to a high intensity beam. So the steps we took to attenuate the beam and use an extremely large analysis area was to avoid the ingrowth of the sulfite peak in any analytical artifacts. Okay, so now we can take a look at what the results were. Again, these are the two reference spectra just to keep in your mind as I step through things. And we can take a look at the mid-ocean ridge basalt sample first. So what this plot is showing is the same picture of the transect. This time, the red symbols represent each of the analysis areas that we targeted from 1 through 6. And what I've done in this figure is I've called out the analysis area that's closest to the rim of the pillow. So this is getting as close as we possibly can to the rim of the pillow, but avoiding this thin layer of pelagonite that forms during eruption. Reaction with the seawater during eruption. And then in the green is the analysis area that's closest to the pillow's interior. So basically as far down as we could get into this crystalline portion of the pillow before we had to worry about hitting crystals in our analyses. So what's fascinating about this comparison is that the spectra in both of these two areas looks almost exactly the same. Qualitatively, we really don't see a difference in sulfur XANES spectra in both of these two analyses areas. And it's also the case that there's an extremely small amount of sulfate present, which is consistent with what we expect to see in mid-ocean ridge basalts, but is detectable enough that we know there's a significant amount there. We can do the same exercise in our back arc basalt pillow. So again, this is showing the analysis areas with the point closest to the rim and the point closest to the interior called out to the right. And again, we see that this back arc basalt pillow has a little bit more sulfate present, as we would expect, but that again, the sulfur XANES spectra are indistinguishable from each other. So we really don't see much of a difference. Okay, so that's the qualitative overview of sulfur XANES spectra in both of these, and we don't see much difference, but what can we learn from iron XANES data? So for iron XANES, we are going to focus on the pre-edge region of the spectra. This is using a technique that's based on the calibration of Elizabeth Cottrell. And again, we're focused on this pre-edge multiplet. What this plot is showing is a suite of experimentally synthesized glasses, synthesized at different oxygen fugacities, and so different proportions of Fe3+ and Fe2+. As we grade from more reduced glasses to more oxidized glasses, that the shape of that multiplet changes, and the higher energy multiplet increases in height. The low energy multiplet decreases in height towards more Fe3+ rich glasses. So this is the feature that we're going to take advantage of, and the calibration, as I'll get into, is going to be based on the centroid value of this multiplet. Okay, iron XANES in glasses that don't contain any volatile elements like water is a little bit less prone to causing beam damage. Unfortunately, our glasses do contain appreciable amounts of water. And so just like in sulfur XANES, we have to consider whether or not we're creating any beam damage in our samples. So this is a study that was done a few years ago, looking into the effect of beam damage during iron XANES analyses of hydrous silicate glasses. What this plot is showing is the intensity of the pre-edge doublet, second pre-edge doublet, so that Fe3+ associated pre-edge doublet normalized as a function of the overall flux. And so it's a way to show the ingrowth of that second multiplet as a function of time, and it's showing that it's changing as a result of this beam damage. There's a few interesting details in this plot. So it's showing that at both high flux and low flux, they see this damage. So it's kind of hard to avoid unless you go to extremely low flux. But the most important thing in the case of iron XANES is that it happens so quickly that if you are using a focus beam, it's very easy to completely miss the fact that you're damaging your sample because it can take place on the same time scale as the analysis itself. So with iron XANES, it's even more important to establish before you even start doing analyses on unknowns that you're operating conditions that won't damage your sample. Also interesting to note in the study is that they did try to use a cryo stage to prevent beam damage, but unlike many applications, it actually seems to make the beam damage worse in hydrous glasses. So that meant that for our conditions for iron XANES, we also attenuated the beam as much as we were able to, and we also increased the beam size as much as we were able to. And so we end up with the similar configuration, this time scanning in the iron XANES region, especially making sure to take fine steps in that pre-edge multiplet. And again, we're targeting optically clear glass pools. This is particularly important in the case of iron XANES because many of the crystals that are present in silicate glasses contain a lot of iron. So it's extremely important to analyze crystal-free glass pools if we want an accurate analysis. So again, before we even started getting into our unknowns, we did a similar approach, testing whether or not we were seeing any ingrowth of the second multiplet as a function of time in a glass that we knew contained an appreciable amount of water, so about 1.3 weight%. So this is the results of that test, and you can see that there's very small, if any, trend with respect to time in the ingrowth of this multiplet. So we were able to move forward to applying our unknowns with some degree of confidence, knowing that we tested our conditions in a conservative kind of water-rich case before we applied them to our unknowns. Okay, so we measured iron XANES in the glasses. Again, I'm just showing two spectra as reference when we go into the unknown spectra. The blue and red are two iron XANES spectra, again in that pre-edge region, and the values of ferric iron in both of them span around what we'd expect to see in natural samples. So it's a little bit more subtle than the signal for sulfur XANES. Because the mid-ocean ridge basalt sample was previously studied by Elizabeth Cottrell and Katie Cully, we're going to focus on the back arc basalt sample. So this is the same type of plot, this time showing in red the analysis areas where we did iron XANES in this back arc basalt data. And we can see the same thing is true here. We don't see any qualitative change in the iron XANES spectra as a function of distance from the rim in this transect. So qualitatively, what we're seeing is promising if we're thinking about whether or not this cooling effect is impacting the way we interpret iron XANES data. We don't see any changes in sulfur XANES or in iron XANES, at least qualitatively. And so the next portion of the talk will focus on quantifying those observations and comparing them to models a little bit more rigorously. So before I get into all of that, I will pause again if there's any questions.
Great, thanks. So I thank you very much. I think Yang Hu has a question. Are you ready?
Hello.
Yep.
Yeah.
Go ahead.
Yeah. Thanks for the talk. I just have one question that for those irons, how they are coordinated in your samples? Is like a common octahedral oxide or it's a mixture?
Oh yeah, okay, I see what you mean. It's a mixture. I would have to refer to other literature for the exact breakdowns of how iron's coordinated, changes a little bit as a function of valence state. One of the reasons why the authors took this approach is that the pre-edge doublet here isn't as sensitive to changes in coordination state within, as long as you're calibrating, you're using a calibration suite that's in like a roughly constant compositional range. So you're not in some crazy compositional space. Yeah.
Yeah, okay, thanks.
Mhm.
Matthew, you have another question?
Oh, there's the button. Yeah, it's kind of talking about the radiation damage. It's another unusual feature of it, aside from the fact that cooling makes it worse, is that it's oxidation rather than reduction. And I was wondering if the sample was an air or inert gas.
The samples were analyzed in air. It does seem to be kind of an interesting form of beam damage compared to other observations that people make. The authors interpreted the beam damage as, or their best guess as to the mechanism of beam damage actually had more to do with hydrogen and the evacuation of hydrogen away from the analysis area, which then oxidized the remaining ferric iron. Interestingly, they were able to confirm that by subjecting the samples to extremely high beam fluxes and then going back and making a map of hydrogen content in the sample. And you can actually see differences in the hydrogen content where they did the analysis area. So that's in part what makes it unique compared to other analysis types. I believe Matt was on the paper as well, so he might have some further insight.
Yeah, still might be worthwhile to give a test where you run nitrogen over the surface, see what happens.
Yeah,
I'll say yes. That's an interesting suggestion, Matthew. Right. So one of the complicating things for beam damage here is that the water in these glasses is at a few weight percent, and so it's partially dissociated. So that complicates what is being reduced and driven away.
Right.
Anyway.
So iron may be coordinated partially to OH, for instance.
Exactly. So yeah, exactly.
Yeah. By the way, a nice thing about this method of reading XANES is that it avoids the effect of overabsorption, as you're only looking at the very bottom of the curve.
Right. Right. So let's move. So Lauren Pincus, you have a question?
Yeah, just quick question. Thanks so much for your talk, Michelle. I'm really enjoying. So I have two sort of quick related questions related to, essentially sort of the feasibility of different techniques based upon the sensitivity of these samples to beam damage. So you'd spoken about how we have to use an unfocused beam. I don't know the length, depending on if this was fly or step scanning, the length of time at which these XANES scans were taking. Are you not able to do any XRF mapping on these as well because you can't do a focused beam? And then similarly, thinking about this iron pre-edge features, I'm curious if it's possible to do any HERFD, K-alpha HERFD on these to really improve resolution in the pre-edge region, or if again, this susceptibility to beam damage makes that not possible. Thanks.
Yeah, those are really interesting questions. So I guess to address the first question, I'm sorry, what was the first question again?
Sorry, yeah, the first question was if XRF mapping is possible on these, or if you can't do it because of the lack of focus beam.
Right, okay, thank you. You can do very quick XRF maps on these samples, and for melt inclusions, we normally have to because they're so small that we need to make sure that we're targeting the glassy area. But we do like very quick, very rapid maps, and we also make sure that before and after the maps are done, there's no point where the beam is sitting on the sample, because we know that anything longer than a few seconds, it'll start to impact the analyses area. So we usually end up driving Matt and Tony crazy because we're like very paranoid about how getting the shutter closed right after we do.
Understood.
Yeah. And then the second question.
That That was
Yeah.
the K alpha Herfty for iron.
Oh,
for the
right.
free
Okay.
edge.
I might be able to speak to it more. I suspect that in the case of iron zanes, the fitting uncertainty and the resolution of the spectra is usually much smaller than the uncertainty on the calibration when converting it over to iron. So for the application I'm using it for, I'm not sure it would improve the precision that much, but whether or not you'd be able to extract more information from more of the x-axis fusion might be a question for Matt.
I would say just quickly, we have done iron K alpha Herfty on similar samples, but that to do it at this low incident flux of in the 10 to the 9 range makes Herfty very hard.
That's what I figured. Okay.
Yeah.
Great. Thank you.
And okay, so great. Thank you, Lauren. And then Ryan, do you have a question or a comment?
Hi, hello. Yeah, I was just very curious in the sulfur zanes that you showed. It looked like in your sample data there was a small lower energy feature that wasn't really captured by the sulfide and sulfate reference. I was just curious if there was any discussion about the origin of that. Yeah, that small species that seems to be present in both the near rim and interior.
Yeah, definitely. I can definitely talk to that. It is a feature that's sometimes observed in glass and sometimes not. There's a little bit of debate as to what specifically it's associated with in terms of glass chemistry, but everyone agrees that it's due to iron sulfur complexing. Most people's opinion is that it's related to iron sulfur complexes in the melt. In the melt structure. There's some people that have argued too that it could be due to kind of micro sulfides that are undetectable, which is hard to test, but we don't see much difference in terms of our ability to extract information about sulfur valence state based on whether or not it's present. As I'll get to later in the talk, in general, our ability to quantify sulfur zane spectra is, I'd say, in its infancy for volcanic glasses. And so right now it's kind of within the general uncertainty we're working with, but most people agree that it's due to iron sulfur complexes in some form.
Very interesting. Thank you so much and great talk so far.
Okay, that sounds like a good opportunity to continue.
Okay. Okay, great. Awesome. Thank you for the great question. So yeah, I'll jump into the next step in our approach, which is quantifying the proportion of sulfur in iron, or excuse me, quantifying sulfur in iron valence state in these volcanic glasses and using it to test this initial model that I talked about a little bit more rigorously. So there's two types of spectra that we need to quantify. As I mentioned, we're using a published calibration in the case of iron zanes. So again, this is based on the iron K-edge pre-edge feature that multiply it, and we're using the centroid energy of that pre-edge feature to quantify our results. I did not include any fitting information in this talk, but I'm happy to talk about that more if anyone's interested. The basic takeaway here is that we're able to take advantage of some fairly precise calibrations. This plot is the calibration that we used in this study. It's based on a suite of experimental samples, and it's based on Mossbauer analyses of these same samples. So the x-axis of this plot is the suite of glasses and the ferric ferrous values measured using Mossbauer, and the y-axis is the centroid value measured using iron zanes. And you can see that there's a pair, you can fit a pretty good regression through these glasses and use them to back out ferric ferrous ratios based on the centroid values. So I'm happy to talk about the details of that more, but overall the takeaway is that it's pretty robust, well-documented calibration. As I mentioned, calibrations with sulfur zanes are a definite work in progress. Sulfur zanes in volcanic glasses is, I'd say, still in the development phase a little bit in comparison to iron zanes data. And one of the current challenges is that we don't have a great suite of calibration glasses available like we do for iron zanes. So what I'm showing here is one of the most commonly used calibrations for sulfur XANES. And it uses the same basic idea that most sulfur XANES calibrations do, which is some simple linear combination fitting between two end-member reference spectra. So in this case, they've taken a reduced basaltic glass and an oxidized basaltic glass, and they've calculated estimates of what they would expect the spectra to look like based on some basic proportion and mixing between these two end members. And then they use the area under the peaks associated with both of these two complexes to construct their own sulfur XANES calibration. So as you can see, it works fairly well, and it has the advantage of being fairly straightforward to implement, but it is based on this assumption around this linear mixing of the two spectra. And so that's really the area where we need more work in this field. I'll note that this is a pretty straightforward approach to interpreting and quantifying the spectra. We have tried very similar approaches using more complex peak fitting of the sulfate and sulfide complexes, along with some other features in the spectra. We can get fairly good fit to the spectra, but we still run into the same issue of not having calibration suites to compare it to. And one of the reasons that this has kind of come to a head in the literature in the last few years is that there are authors who have proposed using scaling factors as a way to account for this uncertainty. So some groups have used scaling factors that were developed for organic sulfur compounds and are applying them to silicate glasses because, again, we don't have a reference suite available. So this is an example of some of the scaling factor calibrations. The blue one is one that people in kind of the volcanic glass community have adopted in recent years. If we apply that to an example data set of natural sulfur XANES data, we can see that it does make an appreciable difference in how we're quantifying the sulfur XANES data available. So this is a comparison plot on a 1-to-1 scale of sulfur XANES processed using the scaling factor that was adopted by Nash et al., Nash and colleagues in 2019. And the x-axis shows the same set of glasses processed without that scaling factor. So you can see that particularly in glasses that have kind of a roughly equal proportion of sulfide and sulfate, the scaling factor uncertainty becomes significant. So hopefully, I mean, this is, the good news is that we're working with pretty broad ranges. And so I think our ability to interpret sulfur XANES spectra is in a decent place, but it could be much, much better if we were able to resolve this uncertainty. So it's one of the areas that I'm really interested in improving in the field. Okay, so that is the backstory to how we quantified the spectra for sulfur and iron XANES in these glasses. What this is showing is the results of that processing. So the vertical axis here is showing distance from the pilogram of each analysis area. And just to roughly guide your eye, I'm showing a, photomicrograph of the Mid-Ocean Ridge basalt thin section in the background. On the horizontal axes are the iron and sulfur valence state taken from our spectra in each of these analysis areas. The iron XANES data is in the blue circles, and the sulfur XANES data is in the red squares. And then that line, the blue and red line, show the average of all of these analyses. So observation number one to make here is that we don't see any systematic in either sulfur or iron valence state with depth along this pillow. And if we compare it to our calculations of absolute uncertainty, we see that none of the measured values are outside of that range. And so again, because of that scaling factor uncertainty in sulfur XANES data, we have this kind of odd looking asymmetric uncertainty in the case of the red sulfur XANES data. So in both cases, though, we don't see any variations in sulfur iron valence state outside of uncertainty along this transect. And we can also compare that to what we're able to calculate about cooling rates based on that half-space cooling model that I mentioned earlier in the talk. So the colored dots in this figure are scaled to a cooling rate, scaled to that color bar shown below. So more purple colors closer to the rim, fast cooled, more blue colors closer to the interior, more slowly cooled. And we can compare these cooling rates to what we know about the most common types of glass that people study in our field. So one of those is external independent estimates for the cooling rate of pillow rims and pillow rim glasses that people have worked with in the past. One of them is these melt inclusions that I mentioned in the beginning of the talk. And one of them is experimental apparatuses. So these are the most common tools we use to generate synthetic glasses that we think represent conditions in the Earth's mantle and crust. And what's really useful to observe about our transect is that it spans the range of cooling rates that we expect to see in all of these types of samples. And so as we ask questions about whether or not we see differences in iron and sulfur XANES, we're able to confidently apply them to all of these different types of glasses that we often study. So we can get back to the initial model that I discussed, which is this model of Nash et al. Shown in the black arrow that suggested that there was a very large temperature effect on the equilibrium exchange between sulfur and iron. What this black arrow is showing is our calculation of the kind of worst case scenario cooling effect in this sample. So this is what would happen if you were able to effectively cool the high temperature silicate melt all the way to the glass transition temperature around 700 degrees Celsius. And you can see that it would, you would expect that the both iron and sulfur XANES values would shift to values outside of the measurement uncertainty. So again, black arrows, worst case scenario. The red arrows are calculated the same way, but this time based on an updated model of the temperature effect of the sulfur and iron valence state. This updated model by O'Neill and Maverjeans was based on some direct experimental data that helped fill in the gaps of what we were kind of extrapolating from thermodynamic calculations, and that model predicts a much smaller temperature effect. So although our model is 100% consistent with this smaller temperature effect model, it is much more consistent, and overall the data set's very consistent with a small temperature effect. In other words, a temperature effect that's so small as to be below detection limits in our analyses. So this is the results for this Mid-Ocean Ridge basalt, which again, doesn't have much sulfate in it, and so we wouldn't expect to experience that drastic of a cooling effect. So we can do the same treatment for the back arc basalt pillow, the back arc basalt pillow, which we know has much more sulfate in it, and so we'd expect to experience a more drastic cooling effect. So this is the same plot and same calculation, this time shown for the back arc basalt pillow. So again, iron and sulfur XANES data, and again, arrow showing the kind of maximum cooling effect that you would expect to see. And again, we see the same thing. So our results are not consistent with the model of Nash et al. That proposed this large cooling effect, and are instead much more consistent with a very small temperature effect, so small as to be below detection using our currently available methods. So this is really promising for interpreting sulfur and iron XANES data going forward. We've established a few things through this work. We've established that iron and sulfur XANES don't show, iron and sulfur valence state don't show any systematic changes over the wide range of cooling rates that these samples have experienced, and that this indicates that the sulfur-iron exchange reaction has a temperature dependence that is small enough to be below analytical detection. And perhaps most importantly, to our ability to carry out research studying how our planet operates, this means that iron and sulfur XANES in glasses with different quench rates can be directly compared, and that we can back up this assumption that high temperature melts, volcanic glasses represents the high temperature melts that they came from. So that allows us to get back to this big picture of studying mass exchange within the interior of our planet. So with that, I'll close out. Thank you for your time and attention, and I'm happy to take any questions.
Great, thank you, Michelle. That was wonderful. I see some applause, but if there's any more questions, type them in. I'll start with one. So it seems like getting that effect of sulfur XANES constraints or sulfur XANES to good values of how much total sulfate there is important. Is there any hope, or what do you have to say for getting better ground truth samples or ways of measuring sulfur redox?
Yeah. It is a uncertainty right now that's pretty important, but I do think there's hope. Like, there are methods we can use to solve that issue. The most straightforward would be to assemble a suite of calibration glasses that have sulfur valence state measured via wet chemistry. That is doable, but there's only a few groups in the world that can do it. So there are some groups that are currently working on this that I'm like anxiously waiting their results to come out. So if we had wet chemistry sulfur and sulfur XANES, we'd be able to tackle those problems a little bit more directly, similar to what we do now for iron XANES. I've also talked with Jerry a little bit in ways that I'm super excited about possibly using different spectroscopic approaches to sulfur analyses and silicate glasses to verify those effects a little bit more directly.
Yep. Sounds good. Okay. Any other questions for Michelle? That was great. I think we're getting a little close in time. I see some people are having to head off to whatever the next meeting is. So for those who are left, there will be another, I'll say there's another XF Journal Club coming, I think March 28th, if I have that right. And I think, I'm not sure, I forget who the speaker is, but there will be one in March. And then I think speakers are lined up for a couple months, but if you have ideas for speakers, send email to Jerry to volunteer. And other than that, let's thank Michelle. And if anybody wants to join in a conversation or chat with Michelle for the next few minutes, that'd be great. All right. And I'll stop recording.